Okay, we can start if you are ready.
I can go first.
Okay.
Okay, can everyone see my screen?
Yes.
Okay, all right. So this is my second presentation on accelerators for graph neural networks, particularly focused on sparse matrix operations. So uh, as was required for this presentation, I'll go through some of the stuff again that I previously did. So my name is Alex. I'm a computer science MS, and my particular area of research is security, though I also work in artificial intelligence and some other areas. I work with Dr. Azad, as well as Dr. Lewis and Dr. Bertenthal. My research interests are varied, but right now I'm looking at graph neural networks and how those can be optimized to go lots faster. So graph learning, graphs are all around us. Networks, these are very basic data structures which are very generalizable and can fit a lot of different types of problems that we have in our world, from logistics, networking, security, bioinformatics. If you can think of it, there's usually a way that it can be put inside a graph. And graph neural networks allow us to have a different kind of approach to machine learning on data than classical neural networks, in that they show us the actual links and connections between the nodes and how those interact with one another. We can do neighborhood detection and a variety of things that are useful in all of these fields. Though for a lot of these very large networks and graphs, it's very difficult to get results if you don't have a supercomputer. So it's necessary to kind of have a significant amount of hardware. And in order to kind of mitigate that, there are a lot of people that are working on optimizing how graph neural networks can be trained, and we can learn something from them. So in order to do that, one of the tools that people have been approaching is sparsity. And that's really what my project is about, how we can use sparse matrix operations in order to improve stuff. So as I previously said, we can apply this kind of method to any number of fields, and we can get some really good results from it. So that's really why we want to make an impact at this lower level, because it doesn't just have an impact on one specific area, but it's more of a general optimization that will help to improve the results of a lot of things. So by using sparsity, we can take a graph that has all of these very large connections, that's very dense, and we can kind of reduce those connections and maintain the general structure and idea of what the graph is actually telling us. This reduces the amount of data that it contains. However, the underlying meaning of that data is still kept when we sparsify a graph. So it significantly reduces the amount of memory we need to use when we run our algorithms, as well as the runtime, because there are fewer elements that we're going to need to actually look at. So I'm going to talk a little bit about the preliminary results that I have now achieved in these past 3 weeks. So I've completed the baseline measure for my research. So a general n by n dense matrix multiplier implemented in VHDL. I've tested this with a test bench to ensure that the output of that is correct. And I've continued to write.
So you try to implement a accelerator for graph convolution neural network, right?
Yes. Yeah.
So what do you mean by accelerator?
Okay. Yeah. So the specific operation which I'm optimizing is SPMM and SDDMM. So SPMM is two sparse matrices multiplied together, and the output is a dense matrix. And then this dense matrix is then typically in almost all graph neural networks and in the learning process taken and then put into a SDDMM operation, which is a sampled dense multiplication. So that's taking two dense matrices, multiplying together, and then sampling those certain nodes or elements of that matrix with a sparse matrix. So that's another kind of sparse operation. So this is this pipeline from SPMM to SDDMM is very common amongst graph neural network operations. So the goal is to create a hardware-based accelerator, which rather than having to use a CPU or GPU compute.
Are you writing VHDL?
Yes, in VHDL. So
are you using some established multiplier, or you write actually some multipliers?
Right now, we're just using the base implementation multiplier in VHDL, though.
You don't have those base implementations.
Okay.
Did you write, or you use some other multiplier written by some other guys?
No. So right now, the dense matrix multiplication is a generalized thing. So it just takes an array, which is kind of flattened, that represents a matrix. So if we have an n by n matrix, it's an array of
how many bits do you have in
8-bit.
Each element?
8 bits.
Then you need an 8-bit multiply 8-bit multiplier.
Yeah. Okay. So then that is also something that I can implement then. Though the correctness of the output, at least now, I have been able to verify just with the current
Please notice
implementation.
that now even you have a multiplier, even you have an 8-bit multiplier, 8-bit multiplier, it's an integer multiplier.
Mm.
Everything in your research is a floating point.
Mm.
So you need to figure out how to handle a floating point.
Okay, so floating point multiplier. All right. Okay, so then that will also be something that I can add to what I need to implement. I still have some.
Yeah, you can continue.
Yeah, I still have some stuff to show. So this is just the kind of overview slide of what I have. So this is currently how I have the dense kernel implemented. So this is just for the baseline reference implementation, so that when we have our sparse implementation, we can show that it's improved over that. So we have some elements here, a clock for synchronizing the operations, a reset bit. So when that is toggled, it resets all of the matrices for A, B, and C so that we can do a new computation. A start bit. So by setting that, it starts the computation between A and B. And then C, which is our output matrix that we're storing to, and then a done bit, which is toggled when it's ready to read from the output of the kernel. So that's the general like structure of the element. The specific implementation I have on GitHub, and I have on a slide at the end a link to it for anyone that's interested and would like to look at it. But I won't go into the actual code exactly here, just for the sake of time.
Do you have any output?
Yes. So that's my next slide, actually. So this is an example of how the kernel is actually working. So we're doing an operation here. So we're setting the two matrices A and B here to some integer values, 8-bit ints, unsigned. So here is the point at which these two matrices are assigned for A and B. And then once we reach here, the multiplication has completed and the value is stored into C. The done bit is raised. So we know that the output has been set, and then we can read the output. And that's what we have here in MATC. And I have verified that the multiplication at least is correct. So I feel pretty good about that at least the correctness of the output is right.
Okay,
But
this is good.
yeah, so this needs to be extended though, as you said, to floating point operations because maybe a little bit of oversight on my part, but that is pretty much the critical point of graph neural networks and everything is that everything there is floating point operations. So hopefully that won't take too long and I'll be able to extend that specific part and just place in that specific multiplier into this implementation that I already know works. And hopefully that shouldn't take too long.
Okay.
And then in terms of the sparse kernel, so I have the baseline implementation, but I've also still been working on the sparse kernels. So what I've been particularly working on is trying to get CSR to work. So this is an example of what CSR is, and it's a type of encoding for sparse matrices. So the first column here that we have is a V, and that contains all of the non-zero values that are in this matrix. The second column is the column index, which identifies which column each of these values occur in. And then the row index is a way for kind of separating out these values into chunks. So you can imagine like taking a substring between 0 and 2 of V. So that'll leave you with 10 and 20. And then those values correspond to the columns that are given in column index. So I've just been working in trying to implement that as a type in VHDL, though I had some trouble with that. So I've been looking into other ways to do it, and it's not particularly difficult. It's just a little bit laborious in getting all of the different matrices with their different values, columns, and row indexes to correctly sync up. But that's what I have been working on in terms of the sparse kernel. Those aren't finished yet, so I don't have any kind of outputs for those. And I haven't finalized the structure of the code, but that is just kind of an overview of what's going on there.
Okay. Okay.
Yeah, and
Good.
this
Thank you.
Yeah, this is my updated research timetable. So I hope that in the next week I'll finish the CSR encoding for the kernels, the sparse ones. And then next week, finish the actual logic for the kernels. And finally, in the third week, I want to write some test benches that better show some of the performance gains. So we're going to use larger matrices because these are generalized. I think, yeah. So this generic type in VHDL is actually pretty interesting, and I only just learned about it. So you can use that in order to parameterize some of the like ports that you have on your components. So by giving it that value, we can set how large we want the matrix to be. Right now, I'm only using square matrices just as an implementation, but it can be adapted to do variable height and width matrices, so not square matrices. But that's what I plan on doing, and hopefully that won't take too long. And added to this as well as the floating point multipliers. And here is included a link to the progress that I have so far. Thank you all.
Thank you. Any question to him? If no question, we can move to the next. Thank you very much.
I can go next.
Okay.
Whoops, sorry, that's the wrong camera I just turned on. Let me switch that around. There we go, we got it. And screen shared, cool, we're good. So afternoon, everyone. This is my kind of phase 1 update for my 501 project. To reintroduce myself really quick, my name is Nick LaPlante. I'm a first-year grad student in ISE, focusing on computer engineering. And my project was to kind of recreate, simulate the classic 1973 Atari arcade game, Space Race. So, Pong, table tennis was the first big hit. After that came Space Race. And a big part of my project is to actually run this on real hardware. So why? I really want to get familiar and get some practice using, FPGAs practically in the real world, kind of as an embedded system. And I needed a project that would leverage, different I/O. And, a game has input and has output. So that kind of made sense. And hopefully my idea was, well, if I use like a much older game, 73, the logic will be simple enough to keep my scope kind of low. As I mentioned at the end, I have pulled my scope back a little bit. Some of my longer term goals, like adding multiplayer, because technically the real game was 2-player. I'm going to scrap that and just make it 1-player, but I'll get to that at the end. And in my first presentation, I mentioned using a hobbyist development board. Specifically, I mentioned the RDA7, which is a good board, and I have one now. I got in this little 3D printed case. However, for all the stuff you're going to see today, I didn't use it. There were some shipping delays, global supply chain issues. What are you going to do? It's affecting everyone right now. But luckily, years ago, during my undergrad here at IU, I bought a bunch of hobbyist boards then, and I ended up just using one of those for this temporarily. So that what you're going to see today is running off an older lattice-based FPGA board. Similar specs, kind of a lower end, hobbyist grade board, not anything super cutting edge, but I don't really need anything super high tech for this project. So my goals for phase 1 were to, use some switches, use some LEDs, get an LED blinking, use some lookup tables to get things blinking and working. Registers and flip-flops are also a really important part. Again, that's basic, kind of building block. And then for my switches, if the player's trying to play the game and, they're hitting the button, but the ship isn't moving, that's going to be really annoying. So adding some filter for debounce, just hopefully get the input to be a bit more consistent. And then mess with a 7-segment display. Because I've decided I want to use that for score keeping, because technically in the real game, the score is kind of kept at the bottom near where the player spawns. I just want to use that 7-segment display. It'll be easier, one less thing to have going over to my VGA. And I was overall pretty darn successful. So this is in the IceCube IDE. Because it's a lattice board, it looks a little bit different than a Zilix offering, but functionally it's the same, just looks a little bit different. So for my very first kind of mini project, I just mapped switches to LEDs. You press a switch and LED comes on. Really simple. The point of this for me was to make sure, okay, I can, program it and actually get, code to go to the board and get flashed on there correctly. Then I got a little 3D print case for this too. As we can see, I hit button 1, LED 1 comes on. Button 2, LED 2. Again, really simple, but it worked. So that was neat. Moving on, I wanted to use a lookup table. We'd use those in previous class homework, and I really wanted to make sure I could get those working on the actual hardware. So in the second mini project, I'm basically taking, 2 switches, 1 LED, and saying, all right, AND gate, activate the first LED only when switches 1 and 2 are active. So again, not super difficult, just trying to make sure I can use a lookup table correctly. And if we look here in one of the output reports, one lookup table is being created here. So that was working. And I hit switch 4, nothing happens. Switch 2, nothing happens. I hit them both together here in a second. And the LED comes on. So again, not anything super crazy, just kind of building up over time. Mini project 3 was flip-flops, being able to remember, okay, what was the last button state or the last LED state? So same entities, right? A switch and LED. I did use a clock on this one, which ended up being kind of one of the more challenging parts of all this for me was, working, with the clock cycles. The FPGA on this board is 25 megahertz for the record. That's important later. For right now, basically all I'm saying here is, hey, off the clock process, whenever, whenever it activates or flips on, and that's what this rising edge function is. That's part of IEEE. Whenever, that clock activates or turns on, hey, peek at the switch states and set the register to whatever the, current switch is. And then most importantly, invert the LED state if the current button state does not match what's in the register. And the output of that, oh, and here's the report. We can see I have a couple D flip-flops being used there in the report. Looks something like this. So I hit the button, LED goes out, now let go, it comes back on. You'll notice though, if you pay attention, sometimes the LED works, sometimes it doesn't, sometimes it stutters. That's the D bounce, right? So, when you hit the switch, that bridge connection happens, it takes a millisecond or 2 for it to stabilize. So that's why I was getting those weird false positives. Doing some reading up on debounce, it seems like that's pretty much been an issue since time immemorial. So I went out, and it seems like one of the most common solutions for fixing this is just kind of waiting. So I set my code to wait for about 10 milliseconds, maybe less than I need. Or more, I'm not really sure. 10 milliseconds seemed to work, so I just kept it there. And this is where the actual timing of the clock comes into play, which was a bit of a challenge. So if I want to wait 10 milliseconds and I'm running at 25 megahertz, I use some online calculators. So that comes out to about a 40 nanosecond period. So then 40 nanoseconds dividing 1 millisecond came out to, what was it? 25,000 cycles. So then I times that by 10, 250,000 cycles. It was about 10 milliseconds for my chip. So that's what this constant kind of max is. So that's how long I want to be waiting. Setting my registers again. Whoops. Then similar, so on the rising edge of the clock, so whenever it's coming on and kind of peaking at current states of things, so if my raw input and the filtered input, because basically I'm just taking, this filter and feeding it to my flip-flop script from back here. So I have the raw and the filtered. And when they don't match, and debounce and that counter hasn't reached its max yet, we iterate, basically just wait a little bit longer, add to the counter, and then, else if, in the syntax for that in VHDL, I thought was kind of weird. ELSIF, that threw me for a minute. Else if, the counter does our register for the counter does equal this constant. Cool, reset it, and then change the, and then go check the states and follow through with the rest, get the LED to come on. And it worked out really well, I think. You can kind of see here, it's quite a bit more consistent. It stutters hardly at all, if any. I'm sure I could mess with this and make it a little bit, better, but that seemed to work out okay. And then the last thing I tried was the 7-segment display, and I didn't totally get this one implemented. I know we talked about in a previous lecture in this class, and in theory it made sense, but actually implementing it on this board, I think a lot of the problem is just me not understanding the way this board was designed. So I dug through a bunch of documentation. For example, one of my big issues was the LEDs on this board activate on being pulled up. Well, the 7-segment display, for some reason, it's set up to pull down. So I need to add an inverter, and that'll fix a lot of my issues, I think. So it's weird little things like that, having to dig through documentation to make sure I understand how the board works and expects to receive things. So my evaluation overall, I think I met most of my phase 1 goals. And I was able to get the hardware to perform kind of as I expected most of the time. And it was a really cool learning experience to figure out, kind of how the clock cycles work and all that, and what this board needs. And so that was really interesting.
So you introduced the 3 to 4 small demonstrations. How did these demonstrations can be, how these demonstrations can be converted to your final project?
Oh, yeah, good question. So let me go back and get a visual demonstration here. So for kind of switch debouncing registers, that's going to be really important for kind of, so the player's little spaceship kind of moving forward. I'll need to know, well, where was the ship currently? Where is it moving to? Lookup tables are going to be really relevant for, oh, if the ship is moving and it's in kind of the same, it's on the same pixel as an asteroid, so if the positions match and these other conditions are met, reset, or if you make it to the end, then we'll need to add a point. And then the 7-segment display, I think I'm going to end up using for the player's point counter, because having it on the screen behind them, it's one less thing I want to have to output over VGA. So to simplify my screen output, I'm just going to have that be on the board. So a lot of this, was kind of building blocks that are going to allow me to actually build the real functionality here during phase 2.
You just showed me some screwdrivers, but eventually you tell me you can make a push, very fancy car. My suggestion is to lower your goal.
Okay. No, I'm open to that. Well, and I did, I am cutting some stuff already. I can cut more if you think that's relevant.
Of course, that's the exactly relevant part.
Right. So no, I'm totally open to that. And I appreciate the feedback. So then phase 2, I was, going to start trying to do some test patterns over VGA and experiment with UART to see if I can get keyboard input for that. However, if I can't get UART or something to work, or if I need to cut something, I can use the onboard switches for that. I have 4 of them, and I know I can get those to work already. The multiplayer I'm cutting, score on the screen I'm cutting, but I can simplify further. So to do that, I would maybe, remove the asteroids, maybe just get the ship kind of moving forward and backwards, just making it to the end. Something like that. So you can still input in the screen updates, but there's going to be a lot less happening there.
Okay,
and then that's the end right there.
Okay, thank you.
Thank you.
Yeah, I mean, the goal of these presentations are just, make sure you know what you are doing right now. Make sure you, at least you think you are on the right track. Thank you. Next one, please.
We can go next. Can everyone see my screen?
Yes.
So we're gonna do our update. So the idea behind our project was to make the dot product as efficient as possible by parallelizing the vector-to-vector computation. The amount of vector-to-vector computation allocated to each core will be based on the amount of cores in the hardware and the size of the weights of the weight matrix.
So the issue that we had over the first phase of the project was basically what we thought we'd have, is that it's really difficult to implement floating point numbers in hardware just because of the way that they're represented. Like if you look at a typical like 32-bit floating point number, like just a float, the way it's formatted is not all like an integer, where basically the representation of it doesn't match for just typical like multiplication or addition even. So like having to use a floating point unit seemed to be like a big issue. And plus I was looking through different forums of people doing that, and even in hardware they usually scale up the floats in software before having it run on hardware, then scale it back down based on the output that the hardware does into software. So it's like a lot of people avoid just doing this in hardware in general just because of how tedious it is. So we decided to go with just simple signed integers. Just had some, I guess, functionality.
So like I said before, we went to integer representation. So like kind of like how we're going to go about this now is we're finishing up setup now. And then we're going to work on the dot product through April 4th through the 10th, and then finishing up return and data the April 11th through the April 17th. Obviously things can go wrong. So we gave us 2 weeks a little to do some documentation, but also to some time for things to go wrong. That way we have the time to go back and fix things and actually get them done. And that is where we're at.
What's your contribution to this project?
I was also doing some research in terms of floating point and also integers, and that also helped with setup as well.
I thought this was the job of Jesus.
We both implemented this together because of issues that we had, and we also made a dot product implementation just to test it could actually be done in hardware. And so far we have that it could be done, and that we actually have done that, and we're going to scale it up for matrix multiplication because that's what's actually used in deep learning.
Okay. Thank you.
All right.
The next, please.
We can go. Okay. Can you guys share my see my screen?
Yes.
Okay. Okay, so this is our second presentation on our 16-bit CPU. Accelerated Master's Program with the specialization in computer engineering. And my partner, Brian, is also majoring in the Accelerated Master's Program for Intelligent System Engineering, and his specialization is cyber physical systems. So our previous schedule is outlined here. In week 1, we were planning and designing all of the components of the CPU, and we began implementing the ALU. In week 2, we kind of finished up the ALU and started testing it and started looking at RAM. And then in week 3, we finished the ALU and its test benches, kind of started looking at RAM again, and then we're investigating the other components of the CPU. So far, as far as work breakdown goes, we've been working together most of the time, but Brian did focus more on the ALU, where I was working more on the memory implementation.
So a little bit about our preliminary results. Overall, our project's mostly on track. We revised the architecture of our project a little bit. And so now the main components of our CPU or micro processor are the ALU, some registers, memory for instructions, the processor controller, and then RAM. So for the ALU, the input is 2 16-bit values, and there's also a 4-bit function select input. This function select will allow up to 16 different functions or choices. However, we wanted to keep it simple to start, and we've implemented 5, which were some logic functions like and, or, greater than, or less than, and then some mathematical things like addition and subtraction. And the addition and subtraction we implemented using a 16-bit ripple carry adder that we created for homework 2. So we brought that into the project. Here's a really simplified version of the ALU test bench just to demonstrate. At the top are the 2 inputs, and then in the middle is the function select, and then the result is at the bottom. The first function is add and then subtract and or and then to see if X or the input 1 is less than input 2. And those were correct. And then for the memory, as I said before, we're implementing like 3 types of data memory. The first one is the instruction memory, and we've kind of implemented at least the first version of all 3 of these. But the instruction memory is read-only and it's constant, and this will store our instructions for our processor. And we plan to have 16 instruction capacity. And then we also created registers, which are 8 16-bit registers. And then the processor will store values here temporarily during various computations. And then finally, the RAM. We're not totally sure if we're going to need this fully yet based on for our project, because we're not going to have extremely long programs with a lot of instructions, but we'll add that if time permits and it's beneficial to our project.
Yeah, so the next steps in making the entire 16-bit CPU is just the overall processor and processor controller. These components kind of bring all of the other elements of our project together, and will handle the reading and writing of instructions to memory, and also allow for the execution of these instructions. We've started these, but are still trying to kind of figure out how everything connects and how we want to design them. But they will basically use certain program instructions based around the MIPS architecture. We're still working on fully writing out the instructions and getting it set, but we do have kind of an example to show what it will look like. So this is like the basic instruction format. There's 3 different fields, basically. There's the R format, which is used when all of the data values in an instruction are located in the registers. And I'll just kind of go through it. OP here stands for the operation code. That's used to select whether like what the instruction is necessarily, like whether it's an add or a subtract or a load. The operation code kind of designates that. And then there's the 2 source registers, RS and RT, and the destination register. And then the function kind of works in coordination with the operation code to select an instruction. And this will be primarily used for like adds and subtracts. And then there's the I format, which is used when an instruction is working with an immediate value or a register address, usually for loads or like storing values in a register. And then the J format is used for a jump instruction, and it has a target address. And to kind of make it make more sense, we added a quick example of an add instruction. So we're adding the values in register 2 and register 3 to the destination register and register 1. And this is kind of what that would look like. It's an R format instruction. The operation code for add is 0. And then it's the register source is 2. And then register 3 is the one we're adding, and we're putting it in register 1. So yeah, just a quick overview of what we're looking to do in the future for our project. But so far, the results have been really good. We were able to successfully implement the ALU. We've also started putting together the instruction memory and the registers. And as you saw, we're starting to plan that out. Going forward, Brian will focus mainly on the implementation of the processor and the controller, and I will be focusing on writing the instructions and the test benches.
Who will implement the RAMs?
What was that?
Yeah, sorry.
Who will implement the RAM?
The RAM, we kind of already have it implemented. We just don't know if we need to
How
figure
about
out.
register?
What the registers?
How
have
about the
also-
registers?
Yeah, we already created those as well. That's kind of, both need to work together to figure out kind of the implementation of the processor and the processor controller to figure out, we got a little stuck on how that all connects, but we just need to spend a little bit more time on it.
Can I
Yep.
say one implemented the ALU? Or both
Yeah.
of you?
I primarily implemented the ALU. Andrew was focusing on implementing memory.
Okay.
But like the overall design of everything, we have been working together most of the time.
Okay, thank you. Thank you very much.
Thanks.
Next group, please.
Can go. Can you see my?
Yes.
Okay. So I am Misuru Ranawaka. So I am a first year master's student, part-time student. So my project is to implement hardware optimized minimal gated units on FPGA to improve the performance of RNN networks. So basically, so this is the minimal gated unit. So it has compared to LSTM and GRU, it has a minimal complexity, and it has only one gate. And basically, this is a higher convergence rate and low memory footprint. So this is the full network architecture. Like what I'm trying to do is create the MGU unit and then MGU set of MGU layers and feed the input vector, and then this network such that it can predict the timestamp. So currently, so these are the VHDL component mapping. So it needs the LUIS multiplier and subtract. It needs the subtract adder and sigmoid generator, and then this gate implementation and the MGU unit. So after that, we need to create MGU cell layers. So all these operations are in floating point as floating point operations. So first, I initially implement this float adder. So basically, the two float numbers, which is 32-bit float numbers, and then it add both and then outputs the result. So okay, so this is the code basically. So it contains the entity float header, and it is the scope and in std logic vector and output this one. So it basically, when we implementing floating point operations, it has a more significant bit, and then we need to get the 8 bits out of that, and the bits for the antecedent. So in the rising edge of the clock, I am do the calculations for the floating point operations. So this is the simulation graph. And then I have implemented the float multiplier. So it is also same as the float adder. So can go to the code. Yes. So here it is the float multiplier. It's same as the float adder, and the multiply operation is the different. So I had to do some kind of approximations here. So kind of rounding. And then the next component is the secret. So basically it takes a value from this vector and then it compares it. So that also I did some kind of approximation for the sigmoid. Here. So basically I divided this mantis into different ranges, and then did the assign some kind of approximated value for that. And then element-wise multiplier. So element-wise, when implementing element-wise multiplier, it takes the float adder as a component. This is the element-wise float multiplier. So this it use the element-wise multiplier, use this float multiplier, and it takes 4 inputs, and it creates an array of float multipliers, and then it maps the post input and outputs, and then it calculates the multiplication of the given vector elements. So this is the output element-wise multiplier, and then the tan generator. So the tan generator is also same as the secret generator, the different operation. And I need a subtractor. So the subtractor always subtract from 1, because in MGU implementation there is a 1 minus operation. So I create subtract from float, and it subtract this value from 1 and the output. And finally the MGU component. So this is the input for the MGU unit, and this is the previous state, and this is the out. So these are 2 inputs, and this is out, and this is the result of the minimal gated unit implementation. If I go to the MGU unit, you can see that it takes this previous input and waits, and the previous state contains all these sigmoid arrays, tan arrays, and element-wise multiplier. So as next steps, I need to create a MGU layer and train the network and do some benchmarking. Yeah, these are the references that I have referred, and that's so.
Thank you. I can see that you basically almost implement every component of your design. The next step is just connect all these components together.
Yeah.
Good, very good. Thank you.
Thank you.
Thank you very much. Any other group? So if no group, we can stop today. Thank you very much. Bye.